There are more numbers between 0 and 1 than there are whole numbers in existence. Not roughly more, not slightly more, infinitely more. A larger kind of infinity, a bigger version of forever, proved with a mathematical argument so short it fits on a napkin and so devastating that the man who discovered it was called a charlatan, a corrupter of youth, and spent his final years in a sanatorium. That result, that some infinities are bigger than others, is the beginning of a story that gets stranger at every turn. The counting numbers, 1, 2, 3, 4, stretching on without end, are the smallest infinity. Above them sits a larger infinity, the infinity of the points on a line. Above that, a larger one still. The tower of infinities rises without limit, each level dwarfing the one below it, and the question of the tower's own structure turns out to be a question that mathematics cannot answer. Not a question nobody has answered yet, a question that has been proved rigorously and permanently to have no answer within the mathematical systems we use. The ancient Greeks were so frightened of infinity that they banned it from mathematics. Medieval theologians declared it an attribute of God and warned that studying it was blasphemy. And when a 19th century mathematician finally looked at it directly, what he found was so strange that his colleagues spent decades trying to make it go away. They failed. The mathematics survived. The mathematician, in many ways, did not. Tonight, we are going to follow infinity from the philosophers who feared it, through the theologians who worshipped it, to the mathematicians who measured it and discovered that it is not one thing but many, and that the many are arranged in a hierarchy so vast that the question of its shape exceeds the reach of proof itself. All of it, slowly, for sleep. The fear of infinity begins with the Greeks. Aristotle, writing in the 4th century before the Common Era, drew a distinction that would dominate Western thinking about infinity for 2,000 years. He distinguished between what he called potential infinity and actual infinity. Potential infinity is a process that can continue without end. You can always add one more, count one higher, divide one more time. The process never finishes, but at every stage, the quantity is finite. You are always on your way to infinity, but never arriving. Actual infinity is different. Actual infinity is a completed totality, an infinite quantity that exists all at once, as a thing, not as a process. The set of all natural numbers considered as a finished collection. The number line, considered as a completed object containing every point simultaneously. Actual infinity is infinity, as a noun, not as a verb. Aristotle allowed potential infinity and rejected actual infinity. You can keep counting forever, he said, but you can never have counted forever. The process is acceptable. The completed result is not. This distinction was not arbitrary. It was rooted in Aristotle's physics, in which the universe is finite, bounded, and comprehensible. An actually infinite quantity would be uncontainable. It couldn't fit within any boundary, couldn't be enclosed by any form, couldn't be comprehended by any mind. In Aristotle's cosmos, everything has a place, a purpose, and a limit. Infinity has none of these. It is the absence of limit, the negation of boundary, the enemy of order. For a philosopher committed to a rational, ordered cosmos, actual infinity was not just wrong, it was threatening. An actually infinite quantity would be unbounded, uncontainable, and threatening to the ordered cosmos that Greek philosophy depended on. The distinction between potential and actual infinity is subtler than it first appears. Consider the natural numbers 1, 2, 3, 4, and so on. In Aristotle's framework, the natural numbers are potentially infinite. You can always name a larger one. The process of counting never terminates. But the collection of all natural numbers, considered as a completed set, is actually infinite, and Aristotle says this collection doesn't exist. You can always count higher. You can never have counted them all. This distinction feels artificial to modern ears, but it had real mathematical consequences. It meant that mathematicians could use infinity in arguments. For any number n, there exists a larger number without committing to the existence of an infinite totality. You could talk about what happens as n grows without bound, without claiming that n ever reaches infinity. The infinity was always in the future, always around the next corner, never present. The ban also shaped how mathematicians thought about the infinite divisibility of space and time. You can always divide a line segment in half, and half again, and half again. The process never ends. But does the line segment contain infinitely many points? Aristotle said no. It contains potentially infinitely many points, meaning you can always find more. But the completed collection of all points doesn't exist as a mathematical object. The band shaped everything. It shaped how mathematicians talked about infinity, how they used it in proofs, and how they avoided it in definitions. When Euclid proved that there are infinitely many prime numbers, he didn't say, the set of primes is infinite. He said, prime numbers are more than any assigned multitude of prime numbers, meaning that for any finite collection of primes, you can always find another one. The infinity is in the process, not in the collection. Euclid was scrupulously Aristotelian. The Pythagoreans, a century before Aristotle, had their own reasons to fear infinity. They believed the universe was built from whole numbers and their ratios. Everything was rational, expressible as a fraction. Then one of them proved that the diagonal of a unit square is irrational. It cannot be written as a ratio of whole numbers. The proof revealed a gap in the number line, a point that no fraction could name. The Pythagoreans, according to legend, drowned the man who discovered this. Whether the drowning is historical or mythological, the reaction it represents is real. Infinity and irrationality were threats to a worldview that depended on order, limit, and comprehensibility. The Greek mathematical tradition produced extraordinary results. Euclid's geometry, Archimedes' calculations of areas and volumes, Apollonius's theory of conic sections, all without ever invoking actual infinity. The method of exhaustion which Archimedes used to calculate the area of a circle by inscribing polygons with more and more sides approaches infinity without claiming to reach it. The polygons get closer and closer to the circle. The approximation gets better and better, but the process is always finite at every stage. The limit is never taken. The infinity is never confronted. For over 2,000 years, Aristotle's ban on actual infinity was treated as mathematical law. Mathematicians used infinity freely as a tool, in limits, in infinite series, in arguments about convergence, but they treated it as a convenient fiction, a shorthand for as large as you like, never as a completed quantity. The ban was reinforced by theology, by philosophy, and by common sense. Infinity was too big, too strange, too dangerous to look at directly. You could use it sideways. You couldn't confront it head-on. The fear was not irrational. The Greeks had good reason to be wary. Infinity does strange things to logic, and the Greeks discovered this the hard way. Zeno of Elea, a contemporary of Socrates, constructed paradoxes showing that infinity could make motion impossible, could make Achilles unable to catch a tortoise, could make an arrow frozen in flight. Zeno's most famous paradox concerns Achilles and the tortoise. Achilles, the fastest runner in Greece, races a tortoise. The tortoise gets start. By the time Achilles reaches the tortoise's starting position, the tortoise has moved ahead slightly. By the time Achilles reaches that new position, the tortoise has moved ahead again. The gap keeps shrinking, but never quite closes. Achilles must complete infinitely many tasks, closing infinitely many gaps, to catch the tortoise, and you can't complete infinitely many tasks. So Achilles never catches the tortoise. Of course, Achilles catches the tortoise easily. The paradox's conclusion is obviously wrong, but the argument seems valid. The answer, which took over 2,000 years to formalize, is that an infinite sum can have a finite total. The time it takes Achilles to close each successive gap forms an infinite series that converges to a finite value. Infinite steps, finite total time. The paradox dissolves once you understand convergent series. The paradoxes weren't mathematical proofs. They were philosophical provocations, designed to expose the contradictions that arise when you take infinity seriously. And they worked. The contradictions were real. The resolution would take 2 millennia. The Indian mathematical and philosophical tradition approached infinity differently. The Jain tradition, which predates Aristotle, explicitly discussed different types of infinity as early as the 6th century before the Common Era. Jain mathematicians classified infinities into categories: infinite in one direction, infinite in 2 directions, infinite in area, infinite in number, infinite everywhere. The Jain classification appears in texts such as the Surya Prajnapti, dating to roughly the 4th century before the Common Era. The categories include innumerable, innumerable, and infinite, with infinite further divided into subcategories based on dimension and direction. The Jains also distinguish between different sizes of infinite sets, a concept that would not appear in Western mathematics until Cantor, 23 centuries later. The Jain mathematician Mahavira, writing in the 9th century, stated that a number divided by 0 is infinite, an early encounter with the relationship between 0 and infinity that remains one of the most delicate points in modern mathematics. Division by 0 is undefined in standard arithmetic, but the limit of 1 over x as x approaches 0 is indeed infinite, and Mahavira was pointing at this connection long before limits were formalized. This classification was philosophical rather than mathematical. It didn't produce theorems or proofs, but it represents the earliest known attempt to treat infinity not as a single monolithic concept, but as a family of related concepts with internal structure. The Jain tradition deserves more recognition than it typically receives in histories of mathematics. The Jain mathematicians were thinking about different types of infinity, at a time when Greek mathematicians were avoiding the concept entirely. The Surya Prajnapti, dating to roughly the 4th century before the Common Era, classifies numbers into innumerable, innumerable, and infinite, and then further classifies the infinite into 5 types based on different dimensions of unboundedness. This is not a casual observation. It is a systematic taxonomy suggesting sustained intellectual engagement with the concept. The Jain contribution to the history of infinity is often overlooked in Western accounts, which tend to trace the story from Greece to Europe with little attention to parallel developments elsewhere. But the Jain tradition represents an independent philosophical engagement with infinity that predates the Greek tradition, and that anticipated, in qualitative terms, the distinctions that Cantor would later make precise. The fact that two civilizations, separated by thousands of miles and centuries of time, independently recognize that infinity has internal structure suggests that the structure is real, that it's a property of mathematics itself, not an invention of any particular culture. The contrast with the Greek tradition is striking. The Greeks feared infinity and banned it. The Indians catalogued it and accepted it. The difference may reflect deeper philosophical orientations. Greek philosophy sought order, limit, and comprehensibility, while Indian philosophy was more comfortable with the unbounded and the ineffable. Whether these cultural attitudes influenced the later mathematical treatment of infinity, or whether the mathematical treatment developed independently of cultural context, is impossible to determine. What we know is that the Indians were thinking about multiple infinities 25 centuries before Cantor proved they exist. In medieval Europe, infinity was theology. God was infinite. God's power was infinite. God's knowledge was infinite. The universe, being God's creation, was finite, bounded, limited, comprehensible to human reason, at least in principle. The infinite belonged to God alone, and human attempts to comprehend it were, at best, presumptuous and, at worst, heretical. St. Augustine, writing in the 4th and 5th centuries, argued that God's mind contains all the natural numbers simultaneously, an actually infinite collection, completed and present, existing as an object of divine cognition. This was a direct contradiction of Aristotle's ban on actual infinity, and Augustine knew it. He resolved the contradiction by declaring that actual infinity, while impossible for human minds, is natural for God. The infinite is not impossible. It is divine. Human mathematics, limited by human cognition, cannot grasp it. But that is a limitation of the mind, not of the mathematics. Augustine was making a surprisingly modern philosophical point. The failure to comprehend infinity says something about the comprehender, not about the infinite. The infinite exists. Our inability to grasp it fully is our problem, not its problem. This theological framing had an unexpected consequence. It kept the concept of actual infinity alive during the centuries when Greek philosophical authority might otherwise have killed it completely. Aristotle said actual infinity doesn't exist. Augustine said it does. In the mind of God, the tension between these two positions kept the question open, simmering beneath the surface of Western intellectual life, waiting for a mathematician brave enough to resolve it. God sees the completed infinity that human eyes cannot. This theological move, relocating infinity from the impossible to the divine, allowed medieval thinkers to acknowledge infinity's existence while keeping it safely beyond human reach. And the divine is beyond human comprehension, so the apparent paradoxes of infinity are simply evidence of the limitations of human reason, not defects in the concept itself. Thomas Aquinas, in the 13th century, refined Augustine's position. Aquinas argued that God's infinity is different in kind from mathematical infinity. God is not infinite the way a number line is infinite, extended without limit in a specific direction. God is infinite in the sense of being unlimited in every perfection simultaneously. Mathematical infinity is a quantitative concept. Divine infinity is a qualitative one. Aquinas used this distinction to maintain both Aristotle's ban on actual mathematical infinity and the theological claim of God's infinity, without contradiction. The scholastic philosophers, the university-based thinkers of medieval Europe, debated questions about infinity with a seriousness and sophistication that is often underappreciated. Can God create an actually infinite object? Can God create a stone so heavy that even God cannot lift it? These questions, which sound like puzzles or jokes, were the medieval equivalent of Cantor's set theory, explorations of the logical structure of infinity conducted within the constraints of the available framework. This theological framing of infinity persisted for 1,000 years. The infinite was God's domain. Mathematics could use potential infinity, the unbounded process, but actual infinity was reserved for the divine. Studying it mathematically was unnecessary at best and impious at worst. Nicholas of Cusa, a 15th century German cardinal, philosopher and mathematician, pushed against this boundary. In his major work, De Docta Ignorantia, on learned ignorance, Cusa argued that the infinite and the finite are related in ways that can be explored, if not fully understood, by human reason. He proposed that an infinite circle and an infinite straight line are one thing, that at infinity, curvature and straightness coincide, distinctions collapse, and opposites merge. Cusa's idea sounds absurd, but it contains a genuine mathematical insight. Consider a circle with a larger and larger radius. As the radius increases without bound, the curvature decreases. A circle with infinite radius would have zero curvature. It would be a straight line. The infinite circle is a straight line. Cusa was right in a sense that he couldn't formalize. This was not rigorous mathematics in any modern sense. It was philosophical mysticism with mathematical flavor, but it represents an early attempt to think about infinity as something other than a theological abstraction or a mathematical taboo. Giordano Bruno, a century later, went further. Bruno argued that the universe itself is infinite, containing infinitely many worlds, each potentially inhabited. This was a direct challenge to the Aristotelian Christian cosmology of a finite, bounded universe with the earth at its center. Bruno was tried by the Inquisition, found guilty of heresy on multiple counts, and burned at the stake in Rome in the year 1600. Bruno's execution was the culmination of an 8-year trial. He was charged with multiple heresies, including denying the divinity of Christ, denying the virginity of Mary, and asserting the infinity of the universe and the plurality of worlds. He refused to recant. According to one account, when the sentence was read, Bruno told his judges, "Perhaps you who pronounce my sentence are in greater fear than I who receive it." Whether his belief in an infinite universe was the primary cause of his execution, or one charge among many, is debated by historians. What is not debated is that infinity was, in 1600, still a dangerous idea. If you are drifting, that is fine. The theologians are done arguing. The stake has gone cold. The history of infinity is, so far, a history of avoidance. The Greeks banned it. The theologians reserved it for God. Everyone agreed it was dangerous. And they were right. It is dangerous, but not in the way they thought. The danger isn't spiritual or theological. The danger is mathematical. Infinity breaks the rules you learned from finite experience, and if you apply finite intuitions to infinite objects, you'll be wrong every time. What comes next is mathematics, the first tentative steps toward looking at infinity directly, without the protection of theology, or the restriction of Aristotle's ban. In 1638, an elderly Galileo Galilei, under house arrest for his defense of the Copernican system, published his final and perhaps most profound work, Discourses and Mathematical Demonstrations, relating to two new sciences. In it, he made an observation about infinity that was simple, devastating, and ahead of its time. Galileo noted that the perfect squares 1, 4, 9, 16, 25, 36, and so on can be put into one-to-one correspondence with the natural numbers. 1 corresponds to 1, 2 corresponds to 4, 3 corresponds to 9, 4 corresponds to 16. Every natural number maps to exactly one perfect square, and every perfect square maps to exactly one natural number. No number is left without a partner. The correspondence is complete. But the perfect squares are also a subset of the natural numbers. They are a part of the whole. Between 1 and 100, there are only 10 perfect squares, but 100 natural numbers. The squares get sparser as the numbers grow. Intuitively, there should be fewer squares than natural numbers. And yet, the one-to-one correspondence shows there are equally many. Every natural number has a square, and every square has a natural number. The part is as large as the whole. The paradox cuts even deeper than it first appears. Not only are there as many squares as natural numbers, but there are also as many even numbers as natural numbers, as many prime numbers, as many multiples of a million as natural numbers. Every infinite subset of the natural numbers, no matter how sparse, can be put in one-to-one correspondence with the full set. The even numbers, 2, 4, 6, 8, are half the natural numbers in density, but there are equally many of them. The primes, which thin out logarithmically, are equally numerous. The multiples of a million, which appear only once every million numbers, are equally numerous. Infinity swallows every attempt to make it smaller. This property, that an infinite set is equinumerous with many of its subsets, is so central to the concept of infinity that Richard Dedekind in 1888 proposed using it as the definition. A set is infinite, Dedekind said, if and only if it can be put in one-to-one correspondence with a proper subset of itself. Finite sets can't do this. Infinite sets can. The property that seems paradoxical is infinity. Galileo found this so paradoxical that he concluded the concepts of equal, greater, and less simply don't apply to infinite collections. Infinity, he said, is a realm where ordinary comparisons break down, where the usual rules of size and containment cease to function. He was right that the result is paradoxical. He was wrong about the conclusion. The concepts of equal, greater, and less do apply to infinite collections, but they need to be redefined. The old definitions, based on counting and comparing totals, don't work when the totals are infinite. New definitions are needed, and the new definitions produce new mathematics. The key new definition is one-to-one correspondence. Two sets are the same size if you compare their elements perfectly. Each element of one set matched with exactly one element of the other. Nothing left over on either side. For finite sets, this agrees with counting. A set of 5 apples can be paired perfectly with a set of 5 oranges, and both have 5 elements. But for infinite sets, the pairing-based definition diverges from the counting-based definition, because infinite sets can be paired with proper subsets of themselves. This is not a defect, it is the definition of infinity. Dedekind in 1888 proposed exactly this as the formal definition. A set is infinite if and only if it can be put in one-to-one correspondence with a proper subset of itself. Finite sets cannot do this. Remove one element from a finite set and it becomes smaller. Remove one element from the natural numbers. Take away, say, the number 7, and the remaining set is still equally large. You can pair each remaining number with a natural number, with nothing left over. The loss of 7 doesn't diminish the set. That's what it means to be infinite. He was wrong about the conclusion. 2 centuries later, Cantor would show that the concepts of equal and greater do apply to infinite collections, but they work differently than you expect, and the results are shocking. Let Galileo's paradox settle for a moment. The part equals the whole. A subset of the natural numbers, the perfect squares, is equal in size as the full set of natural numbers. This isn't a mistake. It's not a trick. It's a defining property of infinite sets. An infinite set can be put into one-to-one correspondence with a proper subset of itself. This property, which Dedekind later used as the definition of infinity, is what makes infinite sets fundamentally different from finite ones. A finite set is always larger than any of its proper subsets. An infinite set is not. Infinity begins where that rule breaks. And once the rule breaks, many other rules break with it. In finite arithmetic, if you add 1 to a number, you get a larger number. In infinite arithmetic, adding 1 to a left null gives you a left null, an equal number. If you multiply a number by 2, you get a larger number. In infinite arithmetic, 2 times aleph null is aleph null. Addition, multiplication, subtraction, all behave differently with infinite quantities. The rules you learned in school don't apply. New rules take their place, and the new rules feel alien until you get used to them. Getting used to them takes time. Even professional mathematicians report that working with transfinite arithmetic requires a kind of mental recalibration, a willingness to accept results that feel wrong until you've verified them logically. The feeling of wrongness doesn't go away with experience. You just learn to trust the logic over the feeling. Galileo's paradox also reveals something about how infinite sets must be compared. With finite sets, you can determine which is larger by counting both and comparing the totals. With infinite sets, counting doesn't work. Both totals are infinity. Instead, you compare by pairing. If every element of set A can be matched with a unique element of set B, with nothing left over, the sets are equal size. If elements of B are always left over, no matter how you pair them, B is larger. This pairing-based comparison is the only method of comparison that works for infinite sets, and it produces conclusions that flatly contradict finite intuition. The even numbers are half the natural numbers in density, but they are equally numerous. The prime numbers thin out logarithmically, but there are equally many primes as natural numbers. The rational numbers are everywhere dense on the number line, yet there are no more rationals than natural numbers. Density and size, which are tightly connected for finite sets, become completely independent for infinite sets. The concept of ordering infinite sets led Cantor to develop a second system of infinite numbers alongside the cardinals. The ordinal numbers describe not how many elements a set has, but how they are arranged. The first infinite ordinal, called omega, represents the natural numbers in their standard order. Omega plus 1 represents the natural numbers followed by a single additional element at the end. Omega plus 2 adds 2 elements. Omega plus omega 2 times omega represents 2 copies of the natural numbers placed end to end. And the ordinals continue upward through omega squared, omega cubed, omega to the omega, and far beyond, into a hierarchy of infinite orderings that is itself richer and stranger than the hierarchy of infinite sizes. The ordinals are important because they describe different ways of being infinite. Two sets can have equal cardinality, an equal number of elements, but different ordinal structures. The natural numbers in their standard order have ordinal omega. The natural numbers rearranged so that all even numbers come first, followed by all odd numbers have ordinal omega plus omega, a different ordering of that set. The distinction between cardinal and ordinal infinity is one of Cantor's subtlest and most important contributions. There is a lesson in Galileo's retreat that would echo through the next 2 centuries. Confronted with a paradox, Galileo didn't resolve it. He surrendered. He said the concepts of comparison don't apply, and he moved on. It was a reasonable response for 1638, but it left the paradox standing, unexplained, waiting for someone with more courage or more tools to confront it. The tools would come, but first, mathematics would spend 2 centuries using infinity without looking at it, the way a hiker crosses a bridge without checking whether the supports are sound. The bridge held, the supports were questionable, and eventually, someone had to go underneath and check. The 17th and 18th centuries used infinity constantly without looking at it directly. Newton and Leibniz built calculus on infinitesimals, quantities infinitely small but not zero, and on limits that approach infinity without arriving. They used infinity as a tool, the way a carpenter uses a saw, with respect for its power and a healthy fear of its edge, but without any need to understand what it's made of. Newton's fluxions involved quantities that were vanishingly small, potential infinitesimals, quantities that were on their way to zero but hadn't arrived. Leibniz's differentials, dx and die, were infinitely small changes. Actual infinitesimals, quantities smaller than any positive number but not zero. Both men used these quantities to produce correct results, and both men struggled to explain what these quantities actually were. The struggle was real. Is dx zero or isn't it? If it's zero, you can't divide by it. If it's not zero, the derivative you calculate isn't exact. The answer, that the derivative is the limit of a ratio as the denominator approaches zero, not the ratio itself when the denominator is zero, resolved the difficulty. But it took 150 years to formalize. During those 150 years, mathematicians used infinity freely, produced extraordinary results, and acknowledged privately that the foundations were shaky. They used infinity as a tool the way a carpenter uses a saw. They didn't examine the saw itself, they examined the wood. This instrumental approach to infinity had a profound consequence. It made infinity useful without making it understood. Engineers, astronomers, and physicists could use calculus to design bridges, predict eclipses, and calculate trajectories, all without committing to any philosophical position about whether infinite quantities actually exist. The mathematics worked. The foundations could wait, and they did wait. For 150 years after Newton, mathematicians used infinity as a tool while avoiding any direct engagement with its nature. The infinite series, the infinite product, the infinite integral, all were treated as limiting processes, never as completed objects. The sum of an infinite series wasn't literally the sum of infinitely many terms. It was the limit that the partial sums approached as you added more and more terms. The distinction is subtle but crucial. One is a completed infinity, the other is a potential infinity. Mathematicians stayed firmly on the Aristotelian side of the line. Cantor was the first mathematician since the Greeks to cross that line deliberately, to treat infinite collections as completed objects, to ask how many elements they contain, and to discover that the answer is not one number but many. The crossing was deliberate, controversial, and permanent. Mathematics never went back. This instrumental approach worked brilliantly. Calculus produced correct results about motion, gravity, heat, light, and sound. The results were verified by experiment. The foundations were questioned by Bishop Berkeley, who called infinitesimals ghosts of departed quantities, but the practical success of the method overwhelmed the philosophical objections. Infinity was useful. Whether it was real was a question mathematicians could defer. Cauchy and Weierstrass in the 19th century replaced infinitesimals with limits, a formalization that eliminated the need to talk about actually infinite or infinitely small quantities. The epsilon delta definition of a limit uses only finite quantities. For every epsilon, there exists a delta. No infinities, no infinitesimals, just ordinary numbers and the relationships between them. The foundations were repaired and calculus could proceed without any commitment to the reality of the infinite. The irony of the epsilon-delta revolution is that it eliminated the need for actual infinity from the foundations of calculus, and then, within a generation, Cantor reintroduced actual infinity into mathematics through a completely different door. Cauchy and Weierstrass had shown that calculus doesn't need actually infinite quantities. Cantor showed that mathematics does. The infinite didn't go away, it moved. The stage was set for Cantor by a growing interest in the foundations of mathematics. What are numbers, really? What is a function? What is continuity? These questions, which had been answered informally for centuries, suddenly demanded precise answers. And the answers, when they came, involved sets, collections of objects, and sets, when you start examining them carefully, lead you straight to infinity. Cantor wasn't looking for infinity when he found it. He was working on a technical problem in analysis, the branch of mathematics that includes calculus. The problem concerned whether certain representations of functions as trigonometric series were unique. In pursuing this question, he needed to understand the structure of certain sets of real numbers, and that understanding required him to compare the sizes of infinite sets. The comparison was supposed to be a technical tool. It became a revolution. And then Cantor arrived, and everything changed. Georg Cantor was born in St. Petersburg, Russia in 1845 to a family of Danish and Russian-German descent. He grew up in Germany, studied mathematics at Zurich and Berlin, and took a position at the University of Halle in 1869. He married Vally Gutmann in 1874 and had 6 children. He was, by the accounts of those who knew him, a devoted father and a passionate musician. He played the violin and was deeply interested in the relationship between mathematics and the arts. The contrast between Cantor's domestic stability and his professional turmoil is one of the poignant features of his story. At home, he was a family man. At work, he was a revolutionary whose ideas provoked hostility from the most powerful figures in his field. The two worlds coexisted uneasily, and as the professional attacks intensified, the domestic peace became harder to maintain. Cantor's father was a successful merchant who moved the family to Germany when Georg was 11. Cantor showed mathematical talent early and studied at the University of Zurich and the University of Berlin, where he was influenced by Karl Weierstrass, the mathematician who rigorized calculus. Cantor received his doctorate in 1867 with a thesis on number theory and took a position at the University of Halle 2 years later. Halle was a mid-tier university, not the prestigious appointment Cantor had hoped for, and he would remain there for his entire career, despite repeated attempts to secure a position at Berlin or Göttingen. The failure to move to a more prestigious institution was a source of deep frustration and, in Cantor's view, was partly due to Kronecker's active interference. Whether Kronecker actually blocked Cantor's appointments, or whether Cantor's persecution complex magnified normal academic politics into personal vendetta, is debated. What is clear is that Cantor spent his entire career at an institution he considered beneath his talents, producing work of world historical importance in an environment he experienced as hostile and isolating. Cantor's path to the diagonal argument was not direct. He first proved the uncountability of the reals using a different method, an argument based on nested intervals rather than diagonalization. The nested interval proof, published in 1874, shows that given any list of real numbers, you can construct a sequence of nested closed intervals that avoids every number on the list. The intersection of the intervals contains a real number that is not on the list. The proof is correct, but less intuitive than the diagonal argument. The diagonal argument came later, in 1891, and it is the version that is now universally taught. Its elegance and its generality. It applies not just to real numbers, but to any attempt to enumerate a larger set, make it the canonical proof of uncountability. But Cantor discovered the result first through the less elegant method, and only later found the beautiful proof. The beauty came second, the truth came first. This pattern, discovering a result through laborious methods and only later finding the elegant proof, is common in mathematics. The first proof of a theorem is often ugly, technical, and hard to follow. The clean proof, the proof that feels inevitable and transparent, comes later, sometimes decades later, sometimes from a different mathematician entirely. The diagonal argument is one of the most celebrated examples of mathematical elegance, and it was Cantor's second proof, not his first. Cantor developed many of his ideas in correspondence with Richard Dedekind, another German mathematician who was working on the foundations of the number system. Their letters, exchanged over many years, document the development of set theory in real time. Cantor testing ideas, Dedekind offering feedback, both men pushing each other toward greater precision and deeper understanding. The correspondence is one of the most important collections of mathematical letters in history, comparable to the Pascal-Fermat correspondence on probability. Cantor's work on infinity began with a technical question in the theory of trigonometric series, a question about the uniqueness of representations of functions as sums of sine and cosine waves. In pursuing this question, Cantor was led to consider the structure of the set of real numbers, and he discovered something that nobody expected. The real numbers cannot be listed. The natural numbers can be listed: 1, 2, 3, 4, 5, and so on. The list is infinite, but it has a clear starting point, a clear ordering, and every natural number appears exactly once. The rational numbers, the fractions, can also be listed, though the listing is less obvious. Cantor showed that you can arrange all fractions in a grid, with the numerator on one axis and the denominator on the other, and then traverse the grid diagonally, listing each fraction exactly once. The rationals are countably infinite, despite appearing to be vastly more numerous than the naturals. They can be put in a list. Cantor's method is to arrange all positive fractions in a grid, where the rows represent numerators and the columns represent denominators. Then you traverse the grid along diagonal paths. First, the fraction 1 over 1, then 1 over 2 and 2 over 1, then 1 over 3 and 2 over 2 and 3 over 1, and so on, skipping fractions that simplify to ones you've already listed. Every rational number appears somewhere on this path. The listing is complete. The result is counterintuitive. The rational numbers are dense on the number line. Between any two rationals, there are infinitely many more. They fill the line like a fog, occupying every neighborhood, no matter how small, and yet they can be listed. They can be lined up in a sequence, one after another, with nothing missed. The fog, when you examine it carefully, is made of discrete droplets, and the droplets can be counted. The integers, positive and negative whole numbers, are also countable. List them as 0, 1, -1, 2, -2, 3, -3, and so on. Every integer appears exactly once. The even numbers are countable, the odd numbers are countable, the prime numbers are countable, every infinite subset of the natural numbers is countable, and every set that can be listed. Every set whose elements can be arranged in a sequence, even an infinite sequence, is countable. The rationals are countably infinite. You can put them in a list, a sequence, a one-to-one correspondence with the natural numbers. The fact that the rationals are countable is itself surprising. There seem to be vastly more fractions than natural numbers. Between 0 and 1 alone, there are infinitely many fractions. 1/2, 1/3, 2/3, 1/4, 3/4, and so on, filling every gap. The number line is dense with rationals. Between any two rationals, there are infinitely many more, and yet all of them can be listed. The listing requires a clever traversal of a two-dimensional grid, but it works. Every rational number appears somewhere on the list, but the real numbers, all the numbers on the number line, including the irrationals like the square root of 2 and pi, cannot be listed. No matter how you try to arrange the real numbers in a sequence, you will always miss some. The list will always be incomplete. The real numbers are uncountably infinite, a strictly larger kind of infinity than the countable infinity of the natural numbers. The proof is Cantor's diagonal argument, and it is one of the most beautiful and disturbing proofs in all of mathematics. Here is how it works. Suppose, for the sake of contradiction, that the real numbers between 0 and 1 can be listed. Write them as infinite decimal expansions. Number 1, 0.5172039, number 2, 0.38411762, number 3, 0.7205814, and so on, one real number for each natural number, supposedly listing them all. Every number on this list is an infinite decimal expansion, an infinite sequence of digits after the decimal point. The list is supposed to contain all real numbers between 0 and 1. Every single one. If even 1 is missing, the list fails. Now construct a new number as follows. For the first digit after the decimal point, look at the first digit of number 1. It's 5. Choose a different digit, say 6. For the second digit, look at the second digit of number 2. It's 8. Choose a different digit, say 9. For the third digit, look at the third digit of number 3. It's 0. Choose a different digit, say 1. Continue. For the nth digit, look at the nth digit of number n and choose something different. The number you've constructed differs from every number on the list. It differs from number 1 in the first digit. It differs from number 2 in the second digit. It differs from number n in the nth digit. It is not on the list. But it is a real number between 0 and 1. So, the list is incomplete. But the list was supposed to be complete. It was supposed to contain every real number between 0 and 1. Contradiction. No matter how you rearrange the list, no matter what ordering you choose, what pattern you follow, the diagonal construction will always produce a number you missed. The argument doesn't attack any particular list. It attacks the concept of listing. It proves that the act of listing, no matter how cleverly executed, cannot capture all real numbers. Therefore, the real numbers between 0 and 1 cannot be listed. They are uncountable. And since the natural numbers are countable, the real numbers constitute a strictly larger infinity than the natural numbers. There are more real numbers between 0 and 1 than there are natural numbers in total. The first time the diagonal argument truly landed for me, not as a proof I could follow step by step, but as something I could feel in my bones. I was sitting at a desk, late at night, writing out the construction by hand. I had read the proof before. I had understood it logically, but this time something shifted. I realized that the argument doesn't just show that one specific list is missing a number. It shows that every possible list is missing a number. No matter how cleverly you arrange the real numbers, no matter what pattern you use, no matter how hard you try, the diagonal construction will always find a number you missed. The uncountability isn't a property of any particular listing. It's a property of the real numbers themselves. They are, in a precise mathematical sense, too numerous to be counted. The word uncountable means exactly this. No sequence, no systematic enumeration can capture all of them. The real numbers overflow any container you try to put them in. They are, in the most literal sense, beyond enumeration. This has a consequence that is easy to state and hard to absorb. Almost every real number is irrational. The rationals can be listed. The irrationals can't. The countable is negligible compared to the uncountable. If you could pick a real number at random, truly at random, with uniform probability across the number line, the probability of picking a rational number would be exactly 0. Not approximately 0. Exactly 0. The rationals, despite being everywhere dense, despite being infinite, occupy no space on the number line. They are a set of measures 0. The number line is almost entirely irrational, and the irrationals can't be listed, and the full set of real numbers is a larger infinity than anything you can count. And too numerous to be counted is what uncountable means. What does it mean for one infinity to be bigger than another? It means there is no one-to-one correspondence between them. If you compare every element of set A with a unique element of set B and have elements of B left over, then B is bigger. If you compare them perfectly with nothing left over, they are equally numerous. This definition of size, called cardinality, is the only one that makes sense for infinite sets, and it produces results that violate every intuition trained on finite experience. The natural numbers and the even numbers have equal cardinality. You can pair each natural number n with the even number 2n, with nothing left over. The natural numbers and the rational numbers have equal cardinality. Cantor's diagonal traversal pairs them perfectly, but the natural numbers and the real numbers do not have equal cardinality. The diagonal argument proves no pairing can work. The real numbers are genuinely, provably, irreducibly more numerous than the natural numbers. Not more numerous in the sense of having a higher density. More numerous in the sense that no function, no matter how clever, can connect them one-to-one. The diagonal argument is often described as a proof about real numbers, but its significance is much broader. The argument works for any domain where you can construct a diagonal element that differs from every entry on the list. It proves that the set of all subsets of the natural numbers is uncountable. It proves that the set of all functions from natural numbers to natural numbers is uncountable. It proves that the set of all infinite binary sequences is uncountable. Each of these results follows from a diagonal construction essentially identical to Cantor's original. The argument also connects to fundamental results in logic and computer science. Alan Turing's proof that the halting problem is unsolvable, that no computer program can determine, in general, whether another program will halt or run forever, uses a diagonal argument structurally identical to Cantor's. Kurt Gödel's proof of the incompleteness of arithmetic uses a similar self-referential construction. The diagonal argument is not just a proof about infinity. It is a proof technique that reveals limits. Limits on what can be listed, what can be computed, what can be proved. That realization that some infinities are genuinely, provably, irreducibly larger than others is the most important single idea in the mathematics of infinity. Everything that follows depends on it. The impact of this result on mathematics cannot be overstated. Before Cantor, mathematicians had one concept of infinity: the unbounded, the limitless, the endlessly large. After Cantor, they had a spectrum: countable infinity at the bottom, large enough to enumerate the natural numbers, the integers, the rationals, the algebraic numbers; uncountable infinity above it, large enough to fill the number line, to contain every point in space, to encompass every possible function. And the spectrum continues. The power set of the reals is larger than the reals. The power set of the power set is larger still. There is no top. The hierarchy of infinities is itself infinite, rising without bound through levels of increasing vastness, each one as far above the last as the reals are above the naturals. Before Cantor, infinity was a single word for a single concept: the unbounded, the endless, the incomprehensibly large. After Cantor, infinity is a hierarchy, a structure, a landscape with its own geography. There are small infinities and large infinities and infinities between them and infinities beyond all of them, and no top to the tower. The diagonal argument doesn't just prove that the reals are uncountable. It establishes a method, a technique for generating objects that aren't on any given list. And the method applies far beyond the real numbers. Consider the set of all infinite sequences of zeros and ones. Each sequence is a string like 011001110, extending forever. Can you list all such sequences? No. The diagonal argument applies directly. Given any list of binary sequences, construct a new sequence by flipping the nth digit of the nth sequence. The new sequence differs from every sequence on the list. The set of all binary sequences is uncountable. This result connects to the real numbers because every real number between 0 and 1 can be represented as an infinite binary expansion, a sequence of zeros and ones after the binary point. The uncountability of binary sequences and the uncountability of real numbers are two faces of one fact. The diagonal method also connects to the foundations of computer science. Alan Turing's proof that some problems are undecidable, that no computer program can solve them, uses essentially an identical technique. You assume a complete list of all possible programs and then construct a problem that no program on the list can solve. The construction is diagonal. The new problem is designed to differ from the nth program on the nth input. The result is that the set of solvable problems is smaller than the set of all problems, in a sense that directly parallels Cantor's distinction between countable and uncountable. Cantor didn't stop at two sizes of infinity. He proved a theorem, the power set theorem, that generates an infinite hierarchy of infinities, each one strictly larger than the one below. The power set of a set is the set of all its subsets. The set containing 1, 2, 3 has 8 subsets: the empty set, each individual element, each pair, and the full set. In general, a set with n elements has 2 to the n subsets. Cantor proved that this relationship holds even for infinite sets. The power set of any set is strictly larger than the original set. The proof uses a diagonal argument similar to Cantor's original. Suppose you could pair a set S perfectly with its power set. Then for each element x of S, there would be a corresponding subset. Consider the set of all elements x such that x is not in its corresponding subset. This set is itself a subset of S, but cannot correspond to any element by a self-referential contradiction. The power set is always strictly larger. Apply this to the natural numbers. The natural numbers form a countably infinite set. Its power set, the set of all sets of natural numbers, is uncountably infinite, with a cardinality strictly larger than Aleph null, the cardinality of the naturals. Now take the power set of the power set, that's even larger, and the power set of that, larger still. The process never ends. Each level of the hierarchy is strictly larger than the one below, and there is no top. The tower of infinities ascends without limit. Cantor introduced a notation for these sizes. The smallest infinity, the cardinality of the natural numbers, he called Aleph null, using the first letter of the Hebrew alphabet. The next larger cardinal he called Aleph 1, then Aleph 2, Aleph 3, and so on. The subscripts themselves eventually go through all the ordinal numbers, including infinite ordinals, producing a staggering hierarchy of infinite sizes. The response from the mathematical community was volcanic. Leopold Kronecker was not a fringe figure. He was a professor at the University of Berlin, the most prestigious mathematics department in the world. He was an editor of Crell's Journal, one of the leading mathematical publications. His mathematical work was excellent. He made important contributions to number theory and algebra. He was also rigid, dogmatic, and convinced that his philosophical position on the foundations of mathematics was not just correct, but self-evidently so. Kroneker's mathematical philosophy was finitist. Only objects that can be constructed in a finite number of steps from the natural numbers are legitimate. Infinite sets, limits, irrational numbers, all of these were, in Kroneker's view, meaningless abbreviations for finite processes, not genuine mathematical objects. His position was coherent but extreme, and it put him in direct conflict with virtually every major development in 19th century mathematics. He was, in every institutional sense, more powerful than Cantor. Kroneker's objection to Cantor's work was philosophical, not technical. He couldn't find errors in Cantor's proofs. The proofs were correct. Kroneker's position was that the proofs proved nothing because the objects they discussed, infinite sets, uncountable collections, transfinite cardinals, don't exist. Only finite constructions are legitimate mathematics. Everything else is theology dressed up as theorems. Kroneker's campaign against Cantor was sustained and effective. He used his editorial position at Crell's Journal to delay the publication of Cantor's papers. He disparaged Cantor's work in lectures and in correspondence with other mathematicians. He reportedly told colleagues that Cantor's transfinite numbers were a form of mathematical sin, a departure from the constructive, finitist methods that Kroneker considered the only legitimate foundation for mathematics. The personal dimension was brutal. Cantor applied repeatedly for positions at the University of Berlin, where Kroneker held sway. Each application was unsuccessful, and Cantor believed, probably correctly, that Kroneker's influence was the reason. The professional isolation deepened Cantor's depression, which in turn made it harder for him to work, which in turn made his applications less competitive. The cycle was vicious and, for Cantor, inescapable. Other mathematicians were caught in the middle. Some supported Cantor privately, but were reluctant to challenge Kroneker publicly. Dedekind, who understood Cantor's work better than almost anyone, maintained a respectful correspondence with Cantor, but didn't intervene in the institutional politics. Mittag Leffler, the Swedish mathematician who published several of Cantor's papers in Acta Mathematica, provided crucial support, but advised Cantor to avoid unnecessary confrontation, advice Cantor found difficult to follow. Kroneker attacked Cantor personally and professionally. He called Cantor a corrupter of youth. He blocked Cantor's publications and sabotaged his career. He reportedly said that God made the integers, all else is the work of man, meaning that the natural numbers are the only legitimate mathematical objects and that Cantor's infinite sets are meaningless fictions. Henri Poincaré, the leading French mathematician of the era, called set theory a disease from which mathematics would eventually recover. He considered Cantor's work philosophically misguided, arguing that mathematics should concern itself with constructible objects and computable quantities, not with completed infinities that exist only as abstractions. Poincaré's position was not identical to Kroneker's. Poincaré was more nuanced and less hostile as a person, but the conclusion was similar. Set theory was a wrong turn, and mathematics would be better off without it. Hermann Weyl, another major mathematician, initially supported Cantor's work, but later expressed reservations, calling set theory a house built on sand. Even Hilbert, Cantor's most powerful defender, acknowledged that the foundations required careful attention, launching his famous program to prove the consistency of mathematics, a program that Gödel's incompleteness theorems would eventually show to be impossible in its original form. He considered Cantor's work philosophically misguided and mathematically dangerous, a departure from the constructive, computational tradition of mathematics that produced results you could use, toward an abstract, set-theoretic approach that produced results you could only contemplate. Cantor paid a devastating personal price for his discoveries. He suffered his first serious mental breakdown in 1884, at the age of 39. He was hospitalized multiple times over the following decades. The relationship between his mathematical work and his mental illness is debated. Some historians attribute his breakdowns to the stress of professional persecution, while others suggest a genetic predisposition to bipolar disorder that would have manifested regardless. What is not debated is that the combination of revolutionary work and professional hostility took a terrible toll. Between 1884 and his death, Cantor was hospitalized at least 6 times for what appears to have been severe depression, possibly bipolar disorder. During his hospitalizations, he was unable to work on mathematics. During his periods of recovery, he often turned to other subjects. He became obsessed with the authorship of Shakespeare's plays, arguing at great length that the plays were written by Francis Bacon. He also delved into theology, seeking to reconcile his mathematical work on infinity with the concept of divine infinity in Catholic theology. He corresponded with Catholic intellectuals and with Pope Leo XIII's advisors, arguing that transfinite numbers were consistent with Catholic doctrine. The theological turn was not merely a distraction from mathematics. Cantor genuinely believed that his discovery of transfinite numbers had theological significance, that the hierarchy of infinities he had uncovered was a reflection of the infinite nature of God. He saw his mathematical work as a form of worship, an exploration of the divine nature through the only medium that could approach it: mathematics. Cantor wrote to Catholic theologians arguing that transfinite numbers were consistent with Catholic doctrine and that the hierarchy of infinities reflected the hierarchy of divine perfections. Some theologians were receptive, others were suspicious. The relationship between Cantor's mathematics and his theology is one of the most unusual intersections of science and religion in the history of Western thought. An exploration of the divine, and the hostile reception from Kronecker and others felt to him not just like professional rejection, but like a rejection of a spiritual truth. Whether this theological conviction sustained Cantor through his difficulties or contributed to them is impossible to determine. What is clear is that the combination of revolutionary mathematical insight, professional persecution, and mental illness created a vortex from which he could not escape. Cantor spent the last years of his life in a sanatorium in Halle. He died in January 1918 at the age of 72. Within a decade of his death, his work had been accepted as the foundation of modern mathematics. David Hilbert, the most influential mathematician of the early 20th century, declared that "No one shall expel us from the paradise that Cantor has created." The paradise metaphor is apt. Cantor's set theory opened up vast new territories of mathematical thought, territories that felt like paradise to those who explored them, and like heresy to those who didn't. Set theory, the disease Poincaré had diagnosed, became the standard framework in which all of mathematics is expressed. The acceptance of Cantor's work required not just proving his theorems, but building a new foundation for all of mathematics on the concept of sets, the very concept that Kronecker had dismissed as meaningless. The project of axiomatizing set theory was undertaken in the early 20th century by Ernst Zermelo, who in 1908 proposed a set of axioms designed to capture the essential properties of sets while avoiding the paradoxes that had plagued naive set theory. The paradoxes were real and serious. Bertrand Russell had discovered in 1901 that naive set theory, the theory that any definable collection is a set, leads to contradictions. Russell's paradox asks, does the set of all sets that don't contain themselves contain itself? If it does, it doesn't. If it doesn't, it does. The paradox is devastating because it shows that the unrestricted concept of a set is self-contradictory. Zermelo's axioms avoid Russell's paradox by restricting which collections count as sets. You can't just define any collection and call it a set. Sets must be built up from simpler sets using specific operations: union, power set, separation, replacement, each governed by a specific axiom. The axioms are permissive enough to allow all the sets that mathematicians actually use, including Cantor's transfinite cardinals, but restrictive enough to block the paradoxical constructions. Abraham Frenkel refined and extended Zermelo's axioms in the 1920s, producing the Zermelo-Frenkel system, ZF for short, or ZFC when the axiom of choice is included. ZFC is the standard foundation for virtually all of modern mathematics. Every theorem in algebra, analysis, geometry, number theory, topology, and every other branch of mathematics can be derived from the ZFC axioms. The axioms are the bedrock, and infinity, Cantor's infinity, with all its paradoxical properties, is built into them from the start. One of the ZFC axioms, the axiom of infinity, explicitly asserts the existence of an infinite set. Without it, the system would be finitist. With it, the system contains all of Cantor's transfinite hierarchy. The axioms of set theory, formulated by Ernst Zermelo and Abraham Frankl in the early 20th century, are the axioms on which virtually all modern mathematics is built. Cantor was right. His enemies were wrong. The vindication came too late to help him. It always comes too late. If you are drifting, let the infinities settle around you. They aren't going anywhere. They have been there since before anyone counted to one, since before anyone drew a line, since before anyone asked, how many? The natural numbers stretch forward without end. The real numbers fill every gap, uncountably dense. The power sets tower upward, each level vaster than the last. And the continuum hypothesis floats between them, unanswered, unanswerable, a question the axioms can see but cannot reach. If you are still awake, the story goes deeper. We've established that infinity comes in different sizes. The natural numbers are countably infinite. The real numbers are uncountably infinite. The hierarchy extends upward without end. But there is a question sitting at the center of this hierarchy that has haunted mathematics for over 140 years, and the answer to it turns out to be one of the most unsettling results in the history of human thought. The question is this: is there an infinity between the natural numbers and the real numbers? Aleph null is the cardinality of the natural numbers. The cardinality of the real numbers is called C. For the continuum, Cantor proved that C is strictly larger than Aleph null. But how much larger? Is C the next infinity after Aleph null? Is C equal to Aleph 1? Or is there an infinity between them? A set that is larger than the naturals but smaller than the reals? Cantor believed there was no infinity between them. He conjectured that C equals Aleph 1, that the continuum is the smallest uncountable infinity. This conjecture is called the Continuum Hypothesis. Cantor spent years trying to prove it, and the effort consumed him. He would write to colleagues announcing that he had proved the Continuum Hypothesis, only to retract the claim weeks later when he found an error. Then he would announce that he had disproved it, that there is an infinity between the naturals and the reals, and retract that too. The oscillation between proof and disproof, between triumph and despair, tracked his mental state with painful precision. In his letters to Dedekind and Mittag-Leffler, you can watch the oscillation in real time, exultant announcements followed by quiet retractions, confident assertions followed by anxious qualifications. The continuum hypothesis became an obsession that Cantor could neither prove nor abandon. The difficulty is not technical in the usual sense. The continuum hypothesis isn't hard the way a complex integral is hard. It doesn't require advanced techniques or clever tricks. It is hard because it asks about the structure of infinity itself, and the axioms of set theory don't contain enough information to determine that structure. The question is perfectly clear. The answer is genuinely absent from the system. And Cantor, who didn't know this, who couldn't have known it, because the independence results were 60 years in his future, kept searching for an answer that wasn't there. The continuum hypothesis is easy to state. Is C the cardinality of the continuum, equal to Aleph 1? Is the first uncountable infinity the same as the infinity of the real numbers? The question seems like it should have a straightforward answer. Either there's a set between the naturals and the reals, or there isn't. He couldn't. The problem consumed him. He would announce a proof, then retract it. He would announce a disproof, then retract that too. The continuum hypothesis resisted every attack, and the inability to resolve it contributed to his mental anguish. The reason Cantor couldn't prove the continuum hypothesis is that it can't be proved, and the reason he couldn't disprove it is that it can't be disproved. Not because the question is too hard, because the question is too deep. It falls outside the reach of the axioms that mathematics uses to prove things. Kurt Gödel was born in Brno, in what is now the Czech Republic, in 1906. He studied at the University of Vienna and became a member of the Vienna Circle, the group of philosophers and logicians who sought to put all knowledge on a rigorous, empirical foundation. Gödel's incompleteness theorems, published in 1931 when he was 25 years old, undermined the Vienna Circle's program by showing that mathematics itself, the most rigorous discipline of all, is inherently incomplete. Gödel fled Austria after the Nazi annexation and settled at the Institute for Advanced Study in Princeton, New Jersey, where he became close friends with Albert Einstein. The two men walked together every day, discussing physics, logic, and philosophy. Gödel made contributions to general relativity. He found solutions to Einstein's field equations that contain closed time-like curves, meaning that time travel is theoretically possible in certain universes, and he continued working on the foundations of mathematics until his health declined in the 1970s. Gödel was one of the most important logicians in history. He had already shaken the foundations of mathematics with his incompleteness theorems of 1931, which showed that any consistent mathematical system powerful enough to describe arithmetic must contain true statements that can't be proved within the system. Mathematics is incomplete. There are truths it can recognize but can't prove. This result, which shocked the mathematical world, showed the dream of a complete, self-contained mathematical system. A dream pursued by David Hilbert and others is impossible. No consistent system of axioms can prove all the true statements within its domain. There will always be truths that escape the net of proof. The incompleteness is not a temporary limitation. It is a permanent feature of any sufficiently powerful mathematical system, proved with a rigor that leaves no room for doubt or hope of circumvention. This result, along with the work of Alan Turing on computability, represents one of the deepest insights into the nature of mathematical knowledge. In 1938, Gödel turned his attention to set theory and proved that the continuum hypothesis cannot be disproved from the standard axioms of set theory. Gödel did this by constructing a specific model of set theory called the constructible universe, or L, in which the continuum hypothesis is true. The constructible universe contains only sets that can be explicitly defined by formulas, excluding the more exotic sets that the full axioms allow. In this stripped-down universe, every set is definable, the continuum hypothesis holds, and the axiom of choice holds. Gödel showed that if the standard axioms are consistent, then the constructible universe is also consistent, which means you can't use the standard axioms to disprove the continuum hypothesis. It's true in at least one model. If the axioms are consistent, if they don't lead to contradictions, then the continuum hypothesis is compatible with them. You can't use the axioms to show it's false. Paul Cohen was a young mathematician at Stanford University when he proved his result. He was 30 years old, a product of the University of Chicago's mathematics department, and had no previous background in set theory. He had made his name in harmonic analysis, a branch of mathematics related to Fourier series, and he turned to set theory essentially on a dare, because the continuum hypothesis was one of the most famous open problems in mathematics, and he wanted to see if he could make progress on it. He could. The technique he invented, called forcing, is a method for constructing new models of set theory from existing ones. The idea is subtle and technical, but the intuition is this. You start with a model of set theory, a mathematical universe in which all the axioms are true, and you force a new set into the model by adding it along with all its consequences. The new model satisfies all the original axioms, but also contains the new set, which can be chosen to make specific statements true or false. Cohen used forcing to construct a model in which the continuum hypothesis is false, a universe where there is an infinity between the naturals and the reals. Since the axioms are equally compatible with this model and with Gödel's constructible universe where the hypothesis is true, neither proof nor disproof is possible within the standard system. He was 30 years old and had no previous background in set theory. He learned the subject specifically to attack the continuum hypothesis, which he did with a technique he invented called forcing. Forcing is a method for constructing new models of set theory, new mathematical universes, in which specific statements are true or false. Cohen used forcing to construct a model in which the continuum hypothesis is false, proving that it can't be derived from the standard axioms. Cohen received the Fields Medal in 1966 for this achievement. His forcing technique has become one of the most important tools in set theory, used to prove the independence of dozens of other mathematical statements. The technique essentially constructs new mathematical universes, new models of set theory, in which specific statements are true or false, demonstrating that the axioms alone can't determine the truth of those statements. In 1963, Cohen proved the other direction. The continuum hypothesis cannot be proved from the standard axioms either. The axioms are equally compatible with the hypothesis being true and with it being false. The question is independent of the axioms. This is different from being unsolved. An unsolved problem, like the Riemann hypothesis, presumably has a definite answer that nobody has found yet. An independent statement has no answer within the system. It's not that mathematicians aren't clever enough to prove it. It's that the axioms don't contain enough information to determine whether it's true or false. You would need to add a new axiom to decide the question, and mathematicians disagree about which axiom to add, because different axioms produce different and equally consistent mathematical universes. It floats, undetermined, neither true nor false within the standard framework. The second time I felt the ground shift under my understanding of mathematics was when I absorbed what independence means. It means there are mathematical statements that are perfectly well defined. They have a clear meaning. They ask a specific question. They should have an answer, and the answer doesn't exist. Not that nobody has found it, that it doesn't exist within the mathematical system we use. The continuum hypothesis is not unsolved. It is unsolvable in a precise, technical, proven sense. This is different from an open problem like the Riemann hypothesis or the twin prime conjecture, which are presumably true or false, but nobody has proved which. The continuum hypothesis is neither true nor false in the standard system. You can add it as an axiom, or you can add its negation as an axiom, and either way, the resulting system is consistent, as long as the original system was. The question has no answer. The mathematics has a gap. Whether this gap reflects a limitation of the axioms or a genuine indeterminacy in mathematical reality is one of the deepest questions in the philosophy of mathematics. Gödel believed that the continuum hypothesis has a definite truth value, that it's either true or false in the real mathematical universe, and that we simply haven't found the right axioms to determine it. Cohen was more agnostic, and the question remains open, not in the sense that nobody has solved it, but in the sense that the concept of solving it is itself unclear. Cohen's proof of the independence of the continuum hypothesis is one of the most celebrated results in 20th century mathematics. He received the Fields Medal in 1966, the highest honor in mathematics, awarded every 4 years to mathematicians under 40. The citation praised the highest degree of mathematical genius and inventiveness of his forcing technique. The independence result has profound philosophical implications. It means that the standard axioms of set theory, the Zermelo-Fraenkel axioms with the axiom of choice, do not fully determine the universe of sets. There are multiple possible mathematical universes, each consistent with the axioms, and these universes disagree about the continuum hypothesis. In some universes, C equals Aleph one. In others, C equals Aleph 2, or Aleph 17. Or Aleph omega. The axioms allow all of these possibilities. This situation is sometimes called set-theoretic pluralism, the idea that there is no single definitive mathematical universe, but rather a multiverse of possible mathematical realities, each internally consistent, each giving different answers to questions like the continuum hypothesis. The parallel with the multiverse idea in physics, multiple possible universes with different physical laws, is striking, though the connection is metaphorical rather than mathematical. Some mathematicians, following Gödel, believe that the continuum hypothesis has a definite truth value that we haven't yet discovered, that there is one correct mathematical universe, and we just need to find the right additional axioms to pin it down. Others, following Cohen, embrace pluralism and accept that some mathematical questions are genuinely indeterminate. The debate is ongoing and shows no sign of resolution, but it has transformed how mathematicians think about their subject. Before Gödel and Cohen, most mathematicians assumed that every well-posed mathematical question has a definite answer, that every statement is either true or false, and the only question is whether we can find the proof. After Gödel and Cohen, this assumption is no longer tenable. Some statements are independent, some questions are undecidable, some mathematical truths are inaccessible from within the systems we use. This doesn't mean mathematics is arbitrary or uncertain. The vast majority of mathematical statements that mathematicians care about, the statements of number theory, analysis, algebra, topology, are decidable within ZFC. Independence is the exception, not the rule, but it is a real exception, and it forces mathematicians to confront the possibility that their subject has limits, not practical limits that better techniques might overcome, but logical limits that are built into the structure of mathematical reasoning itself. The continuum hypothesis is sometimes described as a question about the size of the real number line, but it is really a question about the structure of infinite power. The real numbers have cardinality C, which equals 2 to the power of aleph null, the number of subsets of the natural numbers. Cantor proved that 2 to the aleph null is strictly greater than aleph null. The continuum hypothesis asks, is 2 to the aleph null the next cardinal after aleph null, or are there cardinals between them? The question is natural, the answer is elusive, and the independence results show that the elusiveness is permanent, at least within the standard axioms. This has led some mathematicians to propose new axioms specifically designed to settle the question. Large cardinal axioms, axioms asserting the existence of cardinals with special properties, can determine the value of the continuum in some models. The axiom of projective determinacy, which has strong connections to the theory of infinite games, also has implications for the continuum, but there is no consensus on which additional axioms, if any, should be adopted. Beyond the aleph numbers and the Beth numbers, set theorists have discovered, or constructed, cardinals of astonishing size and complexity. These are called large cardinals, and they form a hierarchy of their own, extending far beyond anything Cantor imagined. The smallest large cardinals are the inaccessible cardinals. Cardinals so large that you can't reach them by any combination of the operations that the ZFC axioms provide. You can't build an inaccessible cardinal by taking power sets, by taking unions, by any of the standard set theoretic constructions. Their existence can't be proved from ZFC. You have to assume they exist by adding a new axiom. Above the inaccessible cardinals are measurable cardinals, wooden cardinals, supercompact cardinals, huge cardinals, and many others, each defined by increasingly powerful properties and each requiring increasingly strong axioms to assert their existence. The large cardinal hierarchy is itself a tower without a top. For every large cardinal axiom that has been proposed, a stronger one can be formulated. Large cardinals are not abstract curiosities. They have consequences for ordinary mathematics, for the theory of real numbers, for the structure of projective sets, for the determinacy of infinite games. The existence of certain large cardinals implies the truth of certain statements about real numbers that ZFC alone can't prove. The hierarchy of large cardinals provides a hierarchy of mathematical strength, each level unlocking new truths about the mathematical universe. The study of large cardinals is one of the most active areas of modern set theory. It represents the current frontier of humanity's exploration of the infinite, the boundary between what we can prove and what we can only hypothesize about the structure of the mathematical universe. The continuum hypothesis remains the most famous open question in set theory, and its independence makes it the most philosophically charged. It is a question that mathematics can state precisely, can study extensively, and cannot answer, and the inability to answer it is itself a proven mathematical fact. While the continuum hypothesis sits in its limbo, the properties of infinite sets continue to produce results that seem impossible. We've established that infinity comes in sizes, but even a single infinity, the smallest one, aleph null, the countable infinity of the natural numbers, produces behavior so strange that it has become one of the most famous thought experiments in mathematics. Consider Hilbert's hotel, a thought experiment proposed by the German mathematician David Hilbert in a 1924 lecture. Hilbert was not just any mathematician, he was arguably the most influential mathematician of the early 20th century, the man who set the agenda for 20th century mathematics through his famous list of 23 unsolved problems. the man who championed Cantor's set theory against its critics, and the man who sought to place all of mathematics on a firm axiomatic foundation. When Hilbert proposed his hotel thought experiment, he was illustrating the properties of countable infinity for a general audience, and the illustration has become more famous than most of his theorems. The hotel has infinitely many rooms numbered 1, 2, 3, and so on. Every room is occupied. A new guest arrives. Is there room? In a finite hotel, the answer is no. Every room is full. But in Hilbert's hotel, the answer is yes. Ask every guest to move to the room with the next higher number. The guest in room 1 moves to room 2. The guest in room 2 moves to room 3, and so on. Every guest moves. Every guest has a room, and room 1 is now empty. The new guest checks in. And infinitely many new guests arrive. Is there room? Yes. Ask every current guest to move to the room with double their current room number. Room 1 moves to room 2. Room 2 moves to room 4. Room 3 moves to room 6. Now all the odd-numbered rooms are empty, and there are infinitely many of them. The infinitely many new guests check in, one per odd-numbered room. What about infinitely many buses, each containing infinitely many guests? Still room. The hotel's capacity is Aleph null, and Aleph null times Aleph null equals Aleph null. The product of two countable infinities is still countable. You can accommodate a countable infinity of countable infinities and still have, in a sense, the same number of rooms. The hotel never fills up. It can't fill up. No amount of arrivals, no number of buses, no caravan of infinitely many buses each carrying infinitely many guests can overwhelm it. The hotel's capacity absorbs every countable influx. But there is one thing the hotel can't accommodate: an uncountable number of guests. If uncountably many guests arrive, as many as there are real numbers, the hotel finally runs out of room. The distinction between countable and uncountable infinity is the distinction between what the hotel can absorb and what it can't. That's what makes it infinite. The hotel teaches you something about infinite arithmetic that no formula can convey as vividly. In finite arithmetic, m plus 1 is greater than n. Always, no exceptions. In infinite arithmetic, Aleph null plus 1 equals Aleph null. Adding 1 doesn't change the size. Aleph null plus Aleph null equals Aleph null. Doubling doesn't change the size. Aleph null times Aleph null equals Aleph null. Squaring doesn't change the size. The smallest infinity absorbs additions, multiplications, and even exponentiation by finite numbers without growing at all. This is not a flaw in the definition. It is a consequence of the definition that Dedekind proposed, that property that Galileo discovered. An infinite set can be matched with a proper subset of itself. That matching is infinite arithmetic. And infinite arithmetic, once you accept it, is perfectly consistent, perfectly logical, and perfectly alien to every intuition you built from experience with finite quantities. The alienness doesn't go away with familiarity. Mathematicians who work with transfinite arithmetic every day still report moments of vertigo when they encounter a result that violates finite intuition. The mathematics is correct, the intuition is wrong, and the gap between correct mathematics and wrong intuition is the permanent condition of anyone who works with infinity. Hilbert's hotel is not a paradox. It's a demonstration of how infinite sets behave differently from finite ones. In a finite set, the part is always smaller than the whole. In an infinite set, the part can be as large as the whole. Adding one element to an infinite set doesn't change its size. Adding infinitely many elements doesn't change its size. The rules are different. And the different rules are not bugs. They are features, properties that follow logically and inevitably from the definition of infinity. The axiom of choice leads to even stranger consequences. The axiom says that given any collection of non-empty sets, it's possible to choose one element from each set simultaneously. For finite collections, this is obvious, just pick one from each. For infinite collections, it's less obvious, because you can't perform infinitely many acts of choosing in sequence. The axiom says you can. It asserts the existence of a choice function without constructing one. The axiom is independent of the other axioms of set theory. You can take it or leave it without producing a contradiction, but leaving it out cripples large areas of mathematics. Without the axiom of choice, you can't prove that every vector space has a basis, you can't prove that the product of compact spaces is compact, and you can't prove Zorn's lemma, which is used throughout algebra and analysis. Most mathematicians accept the axiom of choice because rejecting it cripples large areas of mathematics. Many important theorems require it, but accepting it leads to the Banach-Tarski paradox, proved in 1924, which says the following: a solid sphere can be cut into 5 pieces, and those 5 pieces can be rearranged, using only rotations and translations, no stretching or distortion, into 2 solid spheres, each identical in size to the original. 2 copies from 1, no new material added, no stretching. The volume of the original sphere is, say, 1 cubic meter. The 2 resulting spheres each have a volume of 1 cubic meter. Where did the extra volume come from? It didn't come from anywhere. The pieces are non-measurable sets, sets to which the concept of volume cannot be coherently applied. They don't have a volume. The notion of conservation of volume, which holds for every physically realizable cutting and rearranging, simply doesn't apply to non-measurable sets. The paradox exploits the gap between the mathematical concept of a set and the physical concept of a piece. 2 copies from 1. No new material added. No stretching, just cutting and rearranging. The pieces are not ordinary pieces. They're infinitely complicated, non-measurable sets that can't be physically realized. You can't actually do this with a ball. The pieces in the Banach-Tarski decomposition are not the kind of pieces you can cut with a knife or a laser. They are infinitely intricate, fractal-like sets whose boundaries are so complicated that the concept of volume of 3-dimensional measure simply doesn't apply to them. They exist only in the mathematical realm as consequences of the axiom of choice, and they have no physical realization. The existence of non-measurable sets, sets to which you cannot assign a consistent size, was first proved by Giuseppe Vitali in 1905, using the axiom of choice. Vitali showed that you can partition the interval from 0 to 1 into uncountably many pieces such that no consistent assignment of lengths to the pieces is possible. The Banach-Tarski paradox extends this phenomenon to 3 dimensions with even more dramatic consequences. The theorem doesn't violate physics, but it shows that the mathematical axioms, when combined with infinity and the axiom of choice, produce conclusions that are wildly counterintuitive. The Banach-Tarski paradox is often cited as evidence that mathematics has gone too far, that the axioms are too permissive, that the axiom of choice should be rejected. Most mathematicians disagree. They accept the paradox as a correct consequence of correct axioms and conclude that infinite sets don't behave like finite physical objects, which was already clear from Cantor's diagonal argument and Hilbert's hotel. The paradox is surprising only if you expect infinite mathematical objects to behave like finite physical objects. They don't, and the Banach-Tarski paradox is the most dramatic illustration of the gap between mathematical infinity and physical reality. Some mathematicians have used the paradox as an argument against the axiom of choice. If accepting the axiom leads to conclusions this absurd, perhaps the axiom should be rejected. But the mainstream response has been different. Accept the axiom, accept the paradox, and recognize that the mathematical universe is stranger than the physical universe. Mathematical objects don't have to obey physical laws. They obey mathematical axioms. And the axioms permit things that physics does not. This distinction between what is mathematically possible and what is physically possible runs through the entire story of infinity. Mathematically, there are infinitely many sizes of infinity. Physically, nobody knows whether any actually infinite quantity exists in the universe. The mathematics is certain, the physics is open. And the relationship between mathematical truth and physical reality is one of the deepest unsolved questions in the philosophy of science. That's what makes them infinite. Does infinity exist in the physical universe? This is a question that mathematics cannot answer, because mathematics deals with abstract structures, not physical reality. But physics has its own relationship with infinity, and the relationship is complicated. General relativity predicts that the center of a black hole contains a singularity, a point where the density of matter is infinite and the curvature of space-time is infinite. The singularity at the center of a black hole is a point where the equations of general relativity produce infinite values, infinite density, infinite curvature. If you take a star with enough mass and compress it beyond a critical threshold, general relativity predicts that the compression continues without limit, producing a point of zero volume and infinite density. The prediction is mathematically precise and physically incredible. Most physicists don't believe these infinities are physically real. They believe the infinities signal a breakdown of the theory, a regime where general relativity is no longer valid and a more complete theory, perhaps a theory of quantum gravity that unifies general relativity with quantum mechanics, is needed. String theory and loop quantum gravity are two candidates for such a theory, and both suggest that the singularity is an artifact of applying a classical theory in a regime where quantum effects dominate. If a quantum theory of gravity is developed, the infinite densities at the centers of black holes might be replaced by extreme but finite values, and the singularities would dissolve. The infinities would be revealed as approximations, the result of pushing a theory past its domain of validity, the way Newtonian mechanics gives infinite forces at zero distance but is replaced by quantum mechanics at very small scales. Quantum field theory, the framework that describes subatomic particles, is plagued by infinities that appear in calculations of particle interactions. A technique called renormalization, developed in the 1940s and 50s by Feynman, Schwinger, and Tomonaga, allows physicists to subtract the infinities in a controlled way and extract finite, testable predictions. The technique works. Quantum electrodynamics, after renormalization, gives predictions that agree with experiment to 12 decimal places, making it the most precisely tested theory in the history of science. The agreement between prediction and measurement is so exact that it would be like predicting the distance between New York and Los Angeles to within the width of a human hair. And yet, the calculation that produces this prediction involves subtracting infinity from infinity to get a finite answer. The infinities cancel, but only because the renormalization procedure is designed to make them cancel. Whether this reflects deep mathematical truth or a convenient trick remains debated. Kenneth Wilson, who received the Nobel Prize in Physics in 1982 for his work on the renormalization group, showed that the infinities of quantum field theory have a physical interpretation. They arise because the theory doesn't know about the structure of space-time at very small distances. When you incorporate that structure, when you acknowledge that physics changes at very short distances, the infinities are tamed. Wilson's work suggests that the infinities are not defects in the mathematics, but signals that the theory needs to be modified at extreme scales. But the infinities that are subtracted away are still there in the mathematics, and whether they reflect a genuine feature of nature or an artifact of the mathematical framework remains an open question. The infinities that appear in quantum field theory are of a different character. When physicists calculate the probability that two electrons will scatter off each other, the straightforward calculation produces an infinite answer. The infinity arises because the calculation sums over contributions from virtual particles at every energy scale, and the sum diverges. Renormalization is the technique of systematically absorbing these infinities into the definitions of physical quantities, mass, charge, coupling constants, so that the remaining predictions are finite and testable. The technique was initially controversial. Richard Feynman, one of its inventors, called renormalization sweeping the infinities under the rug. Paul Dirac, another founder of quantum field theory, never accepted it, calling it ugly and incomplete. But the predictions that emerge from renormalization are extraordinarily accurate. The magnetic moment of the electron, calculated using renormalized quantum electrodynamics, agrees with experiment to 12 decimal places. No theory in the history of science has been tested to such precision. The infinities that are subtracted away during renormalization raise a deep question. Are they artifacts of the mathematical formalism, or do they reflect something real about the physical universe? If the universe has a minimum distance scale, as some theories of quantum gravity suggest, then the sums that produce infinities should be cut off at that scale, producing large but finite values. The infinities would be an artifact of assuming that space is continuous at every scale. Whether space actually is continuous, whether you can always divide a distance in half, forever, without limit, is one of the deepest open questions in physics. If space is continuous, it contains actually infinite quantities, infinitely many points between any two positions, infinitely many moments between any two times. If space is discrete, if there is a smallest possible distance, a smallest possible time, then the physical universe might be entirely finite, and the infinities of mathematics would be abstract structures with no physical counterpart. The Planck length, roughly 10 to the negative 35 meters, is sometimes cited as the smallest meaningful distance. But whether the Planck length represents a genuine granularity of space, or merely the scale at which our current theories break down, is unknown. The question of whether physical infinity exists may depend on physics we haven't discovered yet, and the answer might determine whether the infinities of quantum field theory are real or illusory. The question of whether the universe is spatially infinite, whether it extends forever in all directions, is also open. The observable universe is finite, bounded by the distance light has traveled since the Big Bang. But the universe beyond the observable horizon might be infinite, extending forever with identical properties, or it might curve back on itself, forming a closed finite space with no boundary, like the surface of a sphere, but in 3 dimensions. Current observations are consistent with both possibilities, and it may be impossible ever to determine which is correct because light from beyond the observable horizon hasn't had time to reach us since the Big Bang, and it never will. Some theoretical frameworks, eternal inflation, string theory, suggest that our universe is one of infinitely many, each with different physical constants. The multiverse, if it exists, would be an actually infinite collection of universes. The concept is speculative and may be permanently untestable. If the other universes are causally disconnected from ours, we can never observe them. As you lie here, the infinities are all around you, or they aren't. The universe is infinite, or it isn't. The Continuum Hypothesis is true, or it's false, or it's neither. The questions are open, and some of them may stay open forever. Not because we lack the cleverness to answer them, but because the questions themselves are deeper than any axiom system we've built. Cantor looked at infinity and saw structure where everyone before him saw chaos. He saw sizes where everyone saw a single, undifferentiated concept. He paid for his vision with his sanity and his career, and he was vindicated by a mathematical community that, within a generation of his death, adopted his framework as the foundation of the entire subject. The infinity, he revealed, is stranger than anything the Greeks feared, stranger than anything the theologians worshipped, stranger than anything the casual use of the word infinity in everyday language suggests. It is not one thing, but many. Not a boundary, but a hierarchy. Not a destination, but a landscape. A landscape so vast that the question of its own structure turns out to be unanswerable. The story of infinity is unlike the story of any other mathematical concept. Numbers were invented by every civilization independently. Geometry arose from land measurement. Calculus was driven by the needs of physics. Each of these subjects was created to solve practical problems and then grew beyond its origins. Infinity was different. Infinity wasn't solved, it was confronted. Each generation of mathematicians looked at it, recoiled, and either banned it, theologized it, or used it sideways without looking at it directly. Cantor was the first to stare at it without flinching, and what he saw was so strange and so beautiful that mathematics has never been the same. The strangeness persists, the beauty persists, the incomprehension persists, and the questions persist. Questions about the sizes of infinite sets, about the structure of the set-theoretic universe, about the relationship between mathematical infinity and physical infinity, about the limits of proof and the nature of truth. These questions are not relics of a bygone era. They are active research topics pursued by mathematicians and logicians and philosophers today, using tools that Cantor, Gödel, and Cohen developed and that subsequent generations have refined. We started with the claim that you don't understand infinity. That claim stands, not because you aren't paying attention, not because the explanation is inadequate, but because infinity, by its nature, exceeds everyone's comprehension. It exceeds everyone's comprehension. Cantor got closer than anyone before him, and the effort broke him. Gödel got close enough to prove that some questions about infinity have no answers, and his own mental health deteriorated over the decades. Gödel became increasingly paranoid, convinced that unknown enemies were trying to poison him. He would eat only food prepared by his wife Adele. When Adele was hospitalized in 1977, Gödel stopped eating almost entirely. He died in January 1978, weighing roughly 30 kilograms, of what the death certificate listed as malnutrition and inanition caused by personality disturbance. The greatest logician since Aristotle starved to death because he couldn't trust the world to feed him. The connection between infinity and madness is not causal. Mental illness has biological roots, and attributing Cantor's or Gödel's breakdowns to their mathematical work would be irresponsible. But the pattern is hard to ignore. The two mathematicians who went deepest into the infinite both suffered devastating mental illness. Whether the work contributed to the illness, or whether the illness was coincidental, or whether the same cognitive intensity that made them great mathematicians also made them vulnerable to breakdown, nobody can say with certainty. Cohen proved the independence of the Continuum Hypothesis and lived a long, productive life. But the result, he proved, that a perfectly clear mathematical question has no answer, is itself a kind of intellectual vertigo that doesn't fully resolve, no matter how many times you think about it. The word infinity in everyday language is a metaphor. I have infinite patience means you have a lot of patience. The universe is infinitely complex means it's very complex. These are figures of speech, not mathematical claims. Mathematical infinity is not a figure of speech. It is a precisely defined concept with specific properties that can be proved, properties that contradict every intuition you built from experience with finite quantities. Mathematical infinity is precise, specific, and bounded by rules. Kolmogorov's axioms, Zermelo, Frenkel, set theory, Cantor's cardinality, Dedekin's definition. It is the most rigorously studied concept in mathematics, not the vaguest. The contrast between everyday infinity, loose, metaphorical, impressionistic, and mathematical infinity, tight, axiomatic, paradoxical, is total. When a mathematician says there are infinitely many prime numbers, they mean something exact and provable. For any number you name, there is a prime larger than it. The infinity is not vague or metaphorical. It is a theorem with a proof. Infinity is the horizon of mathematics. You can see it, you can walk toward it. You can study its properties, classify its sizes, prove theorems about its behavior. But you can't reach it. It recedes as you approach, revealing new structure at every level, never arriving, never resolving, never becoming the simple single thing you want it to be. The Greeks were right to respect it. They were wrong to ban it. The theologians were right to sense its depth. They were wrong to claim it as God's exclusive property. And Cantor was right to look at it directly, even though the looking cost him everything. The infinite is there. It has always been there. It will be there after every mathematician who has ever studied it is gone. The infinite is the one concept that grows more mysterious the more you study it. Other mathematical concepts become clearer with familiarity. You learn about numbers, and numbers become intuitive. You learn about geometry, and shapes become transparent. You learn about probability, and chance becomes predictable. But you learn about infinity, and infinity becomes stranger. Every theorem Cantor proved opened more questions than it closed. Every advance in set theory revealed more territory to explore. The subject doesn't converge to a clear picture. It diverges endlessly into deeper complexity. Cantor thought he was answering the question of how big infinity is. Instead, he opened a door into a corridor of rooms, each larger than the last, extending without end. The corridor itself is infinite. The rooms are infinite, and the question of the corridor's structure, how the rooms relate to each other, what the layout of the corridor looks like, whether there are hidden rooms between the visible ones, turns out to be independent of the rules that define the corridor in the first place. There is no known mathematical concept that produces this combination of properties, precise definitions, rigorous theorems, and fundamental indeterminacy about basic structural questions. Numbers are well understood. Geometric shapes are well understood. Even the complex numbers and the topological spaces of abstract mathematics are well understood in the sense that their basic properties are determined by the axioms. Infinite sets are different. Their basic properties are not fully determined by the axioms. The axioms leave room for multiple incompatible realities, and no one knows how to choose between them. And the questions it raises, about the sizes of sets, about the structure of the number line, about the limits of proof, about the nature of mathematical reality, are the deepest questions mathematics has ever asked, and some of them are questions mathematics cannot answer. The infinite has always been there. It was there before Aristotle banned it, before Augustine theologized it, before Cantor measured it. You don't need to understand infinity to fall asleep. The primes understood nothing about themselves when Euclid proved they were infinite. The real numbers have no awareness of their own uncountability. The diagonal argument runs in the abstract, independent of any mind that contemplates it. The mathematics exists whether anyone thinks about it or not. The tower of infinities ascends without end. The continuum hypothesis floats without resolution. The diagonal argument generates missing numbers forever. The counting numbers stretch forward. 1, 2, 3, 4. They never stop. They never arrive. They just keep going, each one followed by another. The simplest infinite process in all of mathematics. Between any two of them, between 3 and 4, between 99 and 100, the real numbers fill every gap with an uncountable density that no list can capture. The continuum is everywhere, and it is everywhere richer than the integers, everywhere denser, everywhere more numerous, in a way that Cantor proved and that the axioms cannot fully describe. Above the continuum, the power sets rise, the set of all sets of reals, the set of all sets of reals, each level strictly larger than the last, ascending through a hierarchy that Cantor discovered and that nobody has found the top of, because there is no top. And the night, like the number line, extends in both directions, without boundary, without limit, without end. And that is more than enough to carry into sleep.